Good morning. I'm going to show a video. You're looking at Rosebud, a mechanical puzzle invented 50 years ago by Stuart Coffin. It is composed of 3 identical pieces and 3 mirror image pieces. When assembled, each piece touches all others, and you see it coming apart and going back together. It can only come apart when all 6 pieces move simultaneously. Stuart Coffin named this coordinate motion. Surprisingly, the pieces move in straight lines without rotation. To fully appreciate this remarkable dance for yourself, you can play with these puzzles at my sales table. I'm going to talk about coordinate motion, and it comes from mechanical puzzles, but I believe it has a much wider scope of interest than puzzles. So I'm actually going to try and use my knowledge of 10 years dealing with coordinate motion puzzles to try and understand them mathematically. I'm not going to talk a whole lot about puzzles themselves. Stuart Coffin is the father of coordinate motion. He literally wrote the book on geometric puzzle design. He came up with the term coordinate motion. He has a definition in his book, which you can read. For the purposes of this presentation, I would rather not use the term puzzle, but you can think of a geometric solid with, that's dissected into a bunch of pieces and replace that by the word puzzle if you want to get mathematical. Today, Stuart Coffin is age 93 years young, and he is still designing puzzles. I've been emailing with him in the past couple months, and it was a great honor to meet him at G4G15. He attended G4G13. He is a wonderful guy. He also shares all his puzzle designs very. In his book, you will find this example, and you can think of the rest of the talk as me generalizing this example to other polygons and polyhedra. And this is basically the simplest 3-piece coordinate motion puzzle. This slider here, the only way to assemble it is to move all 3 pieces together at the same time. So this slider embodies the fact that there's a single parameter which describes the state of this puzzle. It can only come apart in this way. And if we move on to a 4-piece example, we simply, and I'm not going to talk a lot about how I created these. I'm just going to show you these. If you want more detail, I have actually written a paper that I can give you a preprint of. If you sign up on a sheet of paper I have over there, I can give you I can send you a preprint. But this is a 4-piece puzzle or object. And it actually can come apart in 2 different ways. It can come apart horizontally or in Y, and vertically. And you might notice that this is actually not coordinate motion because it only involves 2 groups of pieces moving at the same time. Nonetheless, it's a very common phenomenon when you have coordinate motion objects around, and we'll see it over and over in Coffin puzzles. But now we're going to take the leap to 3D. And this 2D may seem trivial, but 3D is quite complicated. And I managed to generalize this procedure of, I call it the rods and holes procedure of what you do is you dissect the solid into the sum number of pieces as you have faces, and you add these rods and holes, and this is a coordinate motion puzzle made from 6 identical pieces. It can only come apart when all 6 pieces move out at the same time. And notice that the direction each piece is moving is towards the face of the original cube or you can also think of it as towards the vertex of the dual, which is the octahedron. And this works for all the Platonic solids. So you see that there is a connection between coordinate motion and the platonic solids. There's a few things you have to do to make it work out for all of them. And in fact, the octahedron comes apart in halves, just like the square, and is basically, that has a problem. But now I want to move to everybody's favorite, or my favorite polyhedron, because you can apply the same procedure to many polyhedron, uniform. So if we take the rhombic dodecahedron, this is my favorite. We see that it has a two-dimension, or it can come apart in two different ways. And if you watch, there's 12 identical pieces here. And if I move out the horizontal axis, you see 4 groups of 3 pieces moving outward. And this is coordinate motion because there's 4 groups of pieces. And if we go up the vertical axis, we see a different group of 4 pieces. You can see from the colors that they're not the same color. And the first coordinate motion I showed, the pieces are moving toward the vertices of a tetrahedron. The second one, they're moving towards the vertices of the dual of that tetrahedron. And if I go out the diagonal, all 12 pieces move differently, just the sum of those 2 motions, but each piece is moving towards the dual of the rhombic dodecahedron, which is the cuboctahedron. So anyway, one comment. This is the only polyhedron that I have found which has 2 coordinate motion solutions. And this is a way in which the rhombic dodecahedron beats all the platonic solids. None of the platonic solids can do this. So, and let me make one final comment. Your exchange puzzle is a coordinate motion puzzle that I haven't talked about. But I also have a paper exchange which also talks about how it was designed. Thank you.
Thank you.